If you're reading this from a cold room right now, with a heating bill that made you wince last month, what I'm about to show you might genuinely change the way you think about every single window in your home. The trick costs less than a cup of coffee per window, takes about 90 seconds to install, and the thermal science behind it has been validated by building energy researchers at institutions you would actually trust. But here is the part almost nobody talks about. The same principle was understood over a century ago, was weaponized by greenhouse engineers in the 1970s, and then was quietly buried under a mountain of expensive commercial products that do the same thing at 50 times the cost. Stay until the end, because the final twist involves a material NASA developed for spacecraft that is now being combined with this $5 trick to create something building scientists are calling a potential game changer for residential energy poverty. Every winter, hundreds of millions of people in the Northern Hemisphere face the same invisible enemy, and it is not the cold air outside. It is the glass in their windows. Most people think walls are the weakest point in a building's thermal envelope, but a standard single-pane window loses heat roughly 10 times faster than the same area of insulated wall. Windows are responsible for 25 to 30% of all residential heating energy use. That means roughly a quarter of every dollar you spend on heating is literally radiating through glass and vanishing into the sky. In the United Kingdom, the Energy Saving Trust has estimated that replacing all single-glazed windows with double glazing in an average semi-detached home could save around £175 per year. But the cost of professional double glazing installation in that same home can run between £4,000 and £7,000. In the United States, the average cost to replace windows in a mid-sized home ranges from $12,000 to $20,000. For renters, the equation is even worse because you cannot modify windows you do not own, and landlords rarely invest in upgrades they will not directly benefit from. So hundreds of millions of people simply accept the cold draft, turn up the thermostat, and pay the price month after month, year after year. But what if the solution was sitting in a shipping department wrapped around fragile electronics, being thrown into recycling bins by the millions of square feet every single day? Bubble wrap, the exact same material used to protect packages, turns out to be a shockingly effective window insulator, and the physics behind why it works is genuinely fascinating. To understand this trick, you first need to understand how heat moves through a window. There are three mechanisms of heat transfer: conduction, convection, and radiation. Conduction is heat moving through a solid material, molecule to molecule, the way a metal spoon gets hot when you leave it in a pot of soup. Glass is a relatively poor insulator, meaning it conducts heat quite efficiently, which is exactly what you do not want in winter. A single pane of glass has an R value, which is the measure of thermal resistance, of approximately 0.9. For comparison, a standard insulated wall has an R value of 13 to 19. That means your window is roughly 15 to 20 times worse at stopping heat flow than the wall right next to it. Convection is the second mechanism, and this is where things get interesting. When warm indoor air touches the cold glass surface, it cools, becomes denser, and sinks, creating a convective current that continuously pulls warm air from the room toward the glass. You have felt this if you have ever sat near a window in winter and sensed a cold draft, even though the window was completely closed. That draft is not air leaking in, it is your own warm air being cooled and circulated downward by the cold glass surface. Radiation is the third mechanism, and it accounts for a significant portion of heat loss, as warm objects inside the room radiate infrared energy directly through the glass to the cold exterior. Now here's where bubble wrap enters the story and where the science becomes almost elegantly simple. When you press bubble wrap directly against a wet window, the flat side of the wrap adheres to the glass through surface tension of the water, and each individual bubble becomes a tiny sealed pocket of air. Air, when trapped in small volumes and prevented from circulating, is actually one of the best insulators available. The thermal conductivity of still air is approximately 0.025 watts per meter Kelvin, compared to glass at roughly 1.0 watts per meter Kelvin. That means still air insulates about 40 times better than glass. This is the exact same principle that makes double-glazed windows work. 2 panes of glass with a sealed air gap between them. The gap in commercial double glazing is typically 12 to 16 millimeters, filled with air or an inert gas like argon. Bubble wrap, specifically the large bubble variety with bubbles approximately 20 millimeters in diameter, creates an air gap of roughly 12 millimeters, which falls right in the sweet spot for insulation. Research conducted at the Building Research Establishment in the United Kingdom found that applying bubble wrap to a single glazed window increased its insulating performance by approximately 50%. That effectively raises the R value from around 0.9 to approximately 1.4, which approaches the lower end of older double glazed units. A study published in the journal Energy and Buildings analyzed low-cost retrofit insulation strategies and confirmed that bubble wrap window insulation significantly reduced thermal transmittance through single-pane glass. The University of Wisconsin Extension Service, which has studied energy efficiency in cold climates for decades, has recommended bubble wrap as a legitimate short-term window insulation method for low-income households. Now here is the part that most people get wrong. Not all bubble wrap works the same way for this purpose. The standard small bubble wrap used for shipping, with bubbles about 6 millimeters in diameter, provides some insulation, but not nearly as much as the large bubble variety. Large bubble wrap, sometimes called moving wrap or furniture wrap, has bubbles roughly 12 to 25 millimeters across, and these larger air pockets create a more effective insulating barrier. The installation method matters enormously too. You spray a fine mist of water on the glass surface, then press the flat side, not the bubble side, of the wrap against the glass. The water creates a temporary adhesive bond through surface tension that is strong enough to hold the wrap in place all winter, but allows easy removal in spring without any residue. Light still passes through, though it becomes diffused, which means you lose clear visibility but retain roughly 80% of the natural daylight. This makes it ideal for bathroom windows, bedroom windows, north-facing windows, or any glass that does not need a clear view. The real-world results are where this story gets genuinely compelling. In 2012, the Alaska Housing Finance Corporation conducted field tests on low-cost window insulation methods in some of the coldest residential environments in North America. They found that bubble wrap, combined with simple, weather-stripping, reduced window heat loss by up to 50% in single-glazed homes. In rural communities across Alaska, where heating fuel can cost $8 to $12 per gallon, that kind of reduction translated to hundreds of dollars in savings per winter per household. The Cooperative Extension Service at the University of Alaska Fairbanks has continued to recommend bubble wrap window insulation as a cost-effective strategy, particularly for homes where full window replacement is not financially viable. In the United Kingdom, the National Energy Foundation included bubble wrap insulation in its list of affordable warmth measures for fuel-poor households. Fuel poverty, defined as needing to spend more than 10% of household income on energy, affects millions of homes across Europe and North America. For these households, a 30% reduction in heating costs is not a convenience. It is the difference between heating and eating. In Japan, where many older homes still use single-pane glass with aluminum frames, DIY bubble wrap insulation became so popular in the 2010s that hardware stores began selling pre-cut window insulation bubble wrap with decorative patterns. The Japanese product, often marketed as window insulation sheets, uses the same basic principle but adds a slight frosted design so the windows look intentional rather than improvised. In Australia, researchers at the Commonwealth Scientific and Industrial Research Organisation studied passive window insulation strategies for both heating and cooling, and found that trapped air layers on windows provided measurable benefits in both directions, reducing heat gain in summer and heat loss in winter. But here's the twist that makes this story much bigger than a simple DIY trick. If bubble wrap is so effective and the science is so well understood, why is this not standard advice from every energy company, every government housing program, every utility provider? The answer involves economics, aesthetics, and the politics of energy efficiency. The window and glazing industry is worth over $200 billion globally. Companies that manufacture double and triple glazed windows, low emissivity coatings, argon-filled sealed units, and smart glass technologies have enormous financial incentives to promote premium products. A $5 roll of bubble wrap that mimics the basic thermal function of a $300 window is not a message that benefits the industry. Energy companies, particularly in deregulated markets, also have complicated incentives around efficiency. When customers use less energy, utility revenues can decline, which is why energy efficiency programs are sometimes underfunded or narrowly promoted. The aesthetic objection is real too, and this is the criticism most often raised. Bubble wrap on windows looks, well, like bubble wrap on windows. In a culture that prizes clean design and curb appeal, telling homeowners to wrap their windows in packing material feels like a step backward. But for the millions of people choosing between adequate heating and other basic needs, aesthetics is a luxury they cannot afford. There is also a deeper historical irony here. Greenhouse growers discovered the insulating properties of bubble wrap in the 1970s during the energy crisis. When oil prices quadrupled between 1973 and 1974, commercial greenhouse operators faced a brutal choice: heat their greenhouses or go bankrupt. A British horticultural researcher realized that lining greenhouse glass with bubble wrap could reduce heating costs dramatically. By the 1980s, bubble wrap greenhouse insulation was standard practice in commercial horticulture across the United Kingdom, the Netherlands, and parts of North America. The product even got its own designation in the industry, horticultural bubble insulation, and it is still sold specifically for this purpose today. Greenhouse research stations documented that bubble wrap insulation reduced heat loss through glass by up to 50%, mirroring the same results later confirmed in residential applications. Yet somehow, the knowledge stayed in the greenhouse industry and never effectively crossed over to mainstream home energy advice. This is a pattern that shows up repeatedly in the history of appropriate technology, where effective low-cost solutions are known in one domain, but remain invisible to the people who need them most in another. Now here is where the story takes its most exciting turn. Modern materials. Science is starting to merge this old principle with cutting-edge technology. Researchers at institutions including MIT and Stanford have been developing transparent aerogel insulation, a material that traps air in nanoscale pores and achieves insulation values many times higher than conventional air gaps. In 2019, MIT researchers published a paper demonstrating a transparent aerogel sheet that could be applied to windows, achieving an insulation performance equivalent to triple glazed windows while remaining see-through. The aerogel works on the same fundamental principle as bubble wrap, trapping air in small, sealed volumes, but it does it at a scale millions of times smaller. The MIT team estimated that widespread adoption of transparent aerogel window insulation could reduce building heating energy consumption in the United States by up to 10%. Meanwhile, companies like View Inc. and Heliotrope Technologies have developed electrochromic smart glass that can change its tint to control solar heat gain, but these products cost hundreds of dollars per square foot. The contrast is striking. A $5 bubble wrap solution and a $500 per panel smart glass solution both address the same fundamental problem of uncontrolled heat transfer through windows. In 2023, researchers at the University of Colorado Boulder published work on radiative cooling films that can be applied to windows and actually emit heat as infrared radiation into space, potentially providing passive cooling without any energy input. These films, combined with winter insulation layers like bubble wrap, could create a seasonal window management system that saves energy year-round for almost no cost. The European Union's Building Performance Directive, updated in 2024, has pushed member states to accelerate building energy retrofits, and low-cost measures like window insulation films and secondary glazing are increasingly recognized as first-step interventions. In the United States, the Inflation Reduction Act passed in 2022 includes provisions for home energy efficiency tax credits, but the minimum spending thresholds often exclude ultra-low-cost measures like bubble wrap insulation, creating a policy gap that disadvantages the poorest households. Some innovators are trying to bridge this gap with products that use the same physics as bubble wrap, but in more socially acceptable forms. Window insulation film kits, sold by companies like 3M and Duck Brand, use a thin plastic film stretched across the window frame and shrunk tight with a hairdryer to create a sealed air gap. These kits cost between $8 and $15 per window and have been shown in testing to reduce heat loss by a similar margin to bubble wrap. The advantage of these film kits is that they are virtually invisible once installed, eliminating the aesthetic objection. The disadvantage is that they are more difficult to install, require careful measurement and cutting, and can be damaged easily. Bubble wrap, by contrast, requires no tools, no measurement precision, and can be repositioned or replaced in seconds. For elderly homeowners, renters, and people with limited mobility, that simplicity is not a minor advantage. It is the entire point. There is another dimension to this story that connects to global climate change. Buildings account for approximately 36% of global energy consumption and nearly 40% of energy-related carbon dioxide emissions, according to the United Nations Environment Program. Heating alone is responsible for roughly a quarter of building energy use in cold climates. If every single glazed window in the world were insulated with even a simple bubble wrap layer, the cumulative reduction in heating energy demand would be measured in hundreds of millions of megawatt hours per year. That is equivalent to taking millions of cars off the road or shutting down dozens of coal-fired power plants. The solution is not a new invention. It is not a startup pitch. It is not a billion-dollar infrastructure project. It is a piece of plastic with air bubbles in it, pressed against wet glass. The thermal dynamics are clear, the field data is consistent, the cost is negligible, and the installation is something a child could do. Yet most people have never heard of it, which tells us something uncomfortable about how information about real solutions travels in a world optimized for selling expensive ones. Now there are limitations, and it is important to be honest about them. Bubble wrap insulation reduces, but does not eliminate heat loss. It will not transform a poorly insulated home into a passive house. It is most effective on single-glazed windows. The benefit on already double-glazed windows is marginal. The diffuse light means it is not suitable for windows where clear visibility is important, like a living room picture window. It should be removed in warm months to allow ventilation and to prevent moisture buildup between the wrap and the glass. In humid climates, trapped moisture can promote mold growth on the window frame if the wrap is left in place year-round without adequate ventilation. It is a seasonal tool, not a permanent solution, but as a seasonal tool, it is remarkably effective for its cost. If you combine bubble wrap on north-facing and secondary windows with a film insulation kit on main living area windows and add simple draft excluders around window frames, you can approach the thermal performance of double glazing across your entire home for under $50. The combination, applied to an average 3-bedroom home with single glazed windows, can realistically reduce heating energy consumption by 25 to 35%. Based on the field data from Alaska, the United Kingdom, and controlled laboratory measurements. The takeaway is not that bubble wrap is the future of building science. The takeaway is that the physics of insulation is fundamentally about trapping air, and you do not need expensive technology to trap air. Nature figured this out long before humans did, which is why polar bear fur is hollow, why bird feathers puff up in winter, why snow itself insulates the ground beneath it. Every one of those natural systems works by creating tiny pockets of still air that resist heat transfer. Bubble wrap does the same thing, crudely, cheaply, and effectively. Sometimes the most powerful technology is not the newest one or the most expensive one, but the one that correctly applies a fundamental principle at the lowest possible cost. The next time you pop a sheet of bubble wrap for fun, consider that you are holding a thermal insulation device that could keep a family warm for an entire winter for less than the price of a fast food meal. That is the kind of hidden knowledge that does not make headlines, does not attract venture capital, and does not win design awards, but quietly changes lives in the coldest months of the year. And maybe that is exactly why it is worth talking about